Hey guys, I'm Craig Enders and thanks for tuning into the Blimp video channel. In this video, I'm going to talk about adding auxiliary variables to a model. The strategy that I'm going to demonstrate is closely related to the saturated correlates model, but it isn't limited to normally distributed variables and it tends to allow a much larger number of auxiliary variables. Before we get started, I want to acknowledge the Institute of Educational Sciences for all their support and point you to the project's webpage. You can download Blimp from the same website. To start, what makes an auxiliary variable an auxiliary variable? At a basic level, we're talking about any variable that does not appear in our focal analysis model. Now, we often have a huge number of candidate auxiliary variables sitting in our data set, so I want to talk a little bit about how to identify good auxiliary variables. As an example, suppose our analysis model is a multiple regression with three predictors, x1, x2, and x3. If our data were complete, no other variables would enter the analysis. However, with missing data, we may want to incorporate additional variables like A, B, or C into our analysis to recapture some of the lost information. Now, we usually have a huge number of candidate auxiliary variables sitting in our data set. And so what makes an auxiliary variable useful to us in a missing data analysis? A classic article from 2001 in the Psychological Methods Journal provides a heuristic for classifying auxiliary variables. I'll describe that classification scheme, and then in a few slides, I'll show you how to do some simple data screening tricks to implement their ideas. Let me start by explaining this path diagram, which demonstrates some of the key ideas from that article. To keep things simple, suppose our analysis involves just two variables, x and y, but y has missing data. The dark blue rectangle labeled m sub y is a binary missing data indicator that codes whether y is observed. This binary variable equals 1 if y is missing and 0 if y is observed. Finally, A, B, and C are potential auxiliary variables. Notice there are two types of associations between the auxiliary variables and the data. The orange arrows are attached to auxiliary variables that contain unique information about y that is not explained by other analysis variables, in this case x. The dark blue arrows are attached to auxiliary variables that predict that missing data indicator. The Collins et al. Article classifies auxiliary variables into three categories according to these associations. That Collins et al. Paper describes what they call type A, type B, and type C auxiliary variables. Type A variables are going to be the most important to us, whereas type C variables are the least important. I'm going to start at the lowest level of the hierarchy with type C variables that we usually want to ignore. Type C auxiliary variables predict whether or not someone is going to have missing data, but they do not explain any unique variation in Y. In the path diagram, variable C predicts missingness, but it is unrelated to the incomplete variable itself. The absence of association with Y is important because it means that type C variables cannot introduce bias, but nor do they contain any information that would sharpen the model's predictions about the missing data. Although it may seem counterintuitive, type C variables are usually not useful as auxiliary variables. The next two levels in the hierarchy, type B and type A auxiliary variables, are ones that we might want to include in our analysis. Category B auxiliary variables share unique or residual covariation with Y, but they do not predict missingness. If that residual association is strong enough, including a category B variable can improve power because the additional correlation helps us sharpen the predictions about the missing scores. Essentially, we can recoup some of the lost information. However, like category C variables, category B variables do not introduce bias if we ignore them. Finally, category A variables correlate with the missing data indicator, but they also contain unique correlation with Y that isn't explained by the analysis. In the path diagram, both types of arrows emanate from A. These are the variables that we really want to be on the lookout for because omitting a type A variable from the analysis can introduce bias. The arrows connecting A to Y and A to M imply that Y and its missing data indicator are correlated because they share a common cause, the auxiliary variable. As long as A is in our model as an auxiliary variable, that correlation is 0 because it's essentially explained away by the additional variable. The conditionally missing at random assumption is satisfied in this case because the unseen score values are uncorrelated with missingness. However, suppose we fail to include a type A auxiliary variable into our analysis. In this case, we induce a spurious correlation between Y and its missing data indicator. The result is a missing not at random process where the unseen score values carry information about missingness. This MNAR mechanism can introduce bias, although the amount of bias depends on the magnitude of that residual correlation. Nevertheless, we want to identify and include category A auxiliary variables if we can find them. The main takeaway from that Collins paper is that useful auxiliary variables have to be correlated with the thing that's missing. However, it's not the bivariate correlation that matters, but rather the residual correlation. Let's take a look at how we can identify possible auxiliary variables that have a residual correlation with our incomplete variables from our analysis. To make the illustration more concrete, I'm going to use data from an educational study. The data set includes assessments of broad reading in first grade and ninth grade, and it also includes teacher ratings of behavioral symptoms and learning problems from the first grade. As a focal model, I'll use a linear regression that has the 3 first grade measures predicting ninth grade reading performance. This is a path diagram and equation for the analysis model. Let me start by fitting a model that doesn't include any auxiliary variables. As a reminder, the missing at random assumption says that the observed data contain all the information that we need to recoup the missing values. We'll eventually expand the scope of the observed data by incorporating auxiliary variables. I explained the Blimp scripting language in another video. The key part of the script is the model command, which lists the outcome variable to the left of the tilde and the predictors to the right. I want to start by looking at the missing data rates because this can narrow our search for auxiliary variables. One thing we know from the literature is that there has to be a substantial amount of missing data in order to benefit from including auxiliary variables. In this analysis, I would focus on the dependent variable read 9, which has about 17% of its observations missing. I wouldn't worry too much about the other variables because there isn't much missing information to recoup. I'll limit the search going forward to auxiliary variables that contain information about the ninth grade reading test scores. As a reminder, it's not the bivariate correlation that matters here, but rather the residual correlation between our ninth grade reading scores and the auxiliary variables. I want to show you some really simple data screening tools that can help you identify the patterns of correlations that we're looking for. To keep the illustration manageable, I'll use 7 auxiliary variables, but the procedure readily scales to a large number of variables. The auxiliary variable set includes 3 binary background variables, math and reading scores from 2nd grade, and a pair of standardized test scores from 7th grade. Notice that the auxiliary variables also have missing data. There's nothing inherently wrong with that, but we want to check whether there are plenty of missing data patterns where the outcome variable is missing when the auxiliary variable is observed. Auxiliary variables have no information to contribute if they are predominantly missing in conjunction with the analysis variables. In my experience, it's often difficult to find good auxiliary variables. Because of that, I don't want to spend a lot of time searching around for extra variables that barely move the needle. I want to show you a procedure that's somewhat approximate, but really quick and easy to apply to a large number of auxiliary variables. I'm going to rely on the residual correlation diagnostics in Blimp. At each MCMC iteration, Blimp computes residuals by subtracting the predicted and observed scores just like we would in a regular regression model. Then it takes that residual data matrix and performs an extra estimation step where it gets the correlations among all of those residuals. This procedure also works for binary variables like the ones we have here, but those residuals are on the latent response score metric. This is a path diagram showing a simplified version of the model that I'm going to fit. There are 3 auxiliary variables in green, and the missing data indicator is in dark blue. I'm explicitly drawing the residual parts of each variable with an ellipse. The orange residual is the part of y that is unexplained by the other analysis variables, literally just y minus y hat. We want to know whether that residual correlates with the auxiliary variables. Since there are no incoming arrows into the green boxes, the green residuals are essentially centered versions of the auxiliary variables. I'm going to define the missing data indicator as a binary variable, so its residuals are going to be on the latent response variable metric. I described categorical variable models in a different video. That secondary model that Blimp estimates includes every possible residual correlation. I show those here with curved arrows. Because the auxiliary variables have missing data, the correlations that result from this procedure could be really noisy and even biased. However, more precise procedures often produce convergence failures as the number of auxiliary variables increases. For that reason, I'm willing to settle for something quick and approximate as a screening device for identifying those correlation patterns from the Collins paper. This is the Blimp script for getting the residual correlations. I'm using labels in the model section as sort of comments here, but these are completely optional. The key line of code at the bottom is a multivariate model for the auxiliary variables and the missing data indicator. All variables inside the curly braces share the same predictor set on the right side of the tilde, which in this case is just the intercept or grand mean. Finally, the rightmost variable inside the braces is the missing data indicator. Appending .missing to the variable's name automatically defines a binary missing data indicator without having to create a new variable in our data set. The nice thing about this approach is that we can readily apply it to other variables in our model. Although the missing data rates don't warrant auxiliary variables for the first grade reading test, we could get its residual associations just by rotating the variables in the analysis model. In this script, I have the first grade reading scores as the outcome and the remaining variables as predictors. The output from this analysis would help us identify auxiliary variables for the incomplete predictor. Now let's take a look at the residual correlation output and link it up to the correlation patterns from the Collins et al. Paper. This is an excerpt from the residual correlation table. There are really two sets of correlations that we care about. First, we have correlations between the residual of our dependent variable and the auxiliary variables, and we also have correlations between the missing data indicator and the auxiliary variables. In the top box, I've highlighted 4 auxiliary variables that show some evidence of residual association with their dependent variable. The highlighted correlations identify variables that could be type A or type B auxiliary variables, but that depends on whether they also correlate with the missing data indicator. Looking at the missingness correlations, only one of the variables, standardized math scores in 7th grade, has any sort of correlation with the missing data indicator. This variable is potentially a category A variable, but the absence of missing data indicator correlations suggests that the others could be type B variables. Without being too discriminating, we could readily include all 4 auxiliary variables in our analysis. Auxiliary variables won't do us any good if they're always missing whenever our analysis variables are missing. We want to go back to the table where Blimp summarizes the missing data patterns so we can make sure that there's adequate coverage. By default, Blimp summarizes the 10 largest missing data patterns. In this case, we get a note saying that it's suppressing 12 missing data patterns, and these patterns consist of about 11% of the data. Our main concern is with the 9th grade reading scores. We can see that there are 2 larger patterns where this variable is incomplete. The M's indicate that a variable is missing, and the dashes indicate that the variable is observed. We're looking to see if the auxiliary variables also have M's in these columns, because those would be patterns where the additional variables didn't carry much information. In this example, the auxiliary variables are predominantly observed when the 9th grade reading scores are missing. This tells us that the auxiliary variables contain information that could be useful in estimating our model. The classic saturated correlates model is somewhat limited because it only handles normally distributed variables, and it tends to produce convergence failures as the number of auxiliary variables increases. I'm going to show you a different strategy that doesn't share those limitations. What we're going to do here is add the auxiliary variables as extra dependent variables, and all of our focal model variables are going to point to those auxiliary variables. This path diagram shows a simplified version of the model that I'm going to fit. There are 2 auxiliary variables in green, and notice that these auxiliary variables are predicted by all analysis variables, including just the main effects is fine, even if the analysis includes interactions or other higher order terms. The other important feature is that the auxiliary variables connect to each other with a regression equation. The order doesn't matter here, and we could also have auxiliary variable 2 predicting auxiliary variable 1. The key is that all possible pathways among the auxiliary variables are accounted for. Because everything is estimated simultaneously, the incomplete variables in the analysis can borrow from the auxiliary variables via these regressions. Although the point estimates and standard errors from our model may change, the focal regression parameters have the same interpretation as they would have had the data been complete. This analysis script incorporates 4 auxiliary variables, one of which is binary. The analysis is going to produce a large number of summary tables that I don't really care about, so I'm using labels inside the model section to order the output tables. My focal model is going to appear first, and then the auxiliary variables will appear in alphabetical order after that. I marked the auxiliary variables with orange typeface so you can see the cascading pattern. First, notice that all 4 analysis variables predict every auxiliary variable. The auxiliary variables also have to link to one another. So the first auxiliary variable predicts the second, the first and the second predict the third, the first three predict the fourth, and so on. The approach is similar in spirit to the saturated correlates model because it does include all possible associations between the analysis variables and the auxiliary variables, as well as all possible associations among the auxiliary variables. However, this extra dependent variable strategy can accommodate a much larger number of auxiliary variables, and it can also incorporate categorical auxiliary variables, as I do here. That model can be a little bit of a pain to specify when we have a large number of auxiliary variables, so I want to show you a shortcut where you can do everything in a single line of code. All we need to do here is list the auxiliary variables to the left of the tilde and put the analysis variables to the right of the tilde. Blimp automatically builds that cascading pattern of regression models for the auxiliary variables that I showed you in the previous slide. Finally, let's take a look at the output and see what changed when we added the auxiliary variables to our analysis. The panel on the left shows the estimates from the model without the auxiliary variables, and the panel on the right reflects the analysis with the auxiliary variables. To reiterate, the interpretations of the regression model parameters are the same in either case. At a high level, the results were pretty consistent, and most of the estimates didn't change much at all. The posterior standard deviations, or Bayesian standard errors, are slightly smaller with auxiliary variables, which is to be expected because we're using more information in the analysis. Although the reductions in noise were pretty small, this is still consistent with what we would expect. The behavioral symptom slope showed the largest change, with the point estimate shifting by about 0.05. This is equivalent to about 1/2 of its standard error or posterior standard deviation. I would characterize that difference as somewhere between modest and moderate. It's important to emphasize that there's no way to know for sure which solution is more correct or closer to the truth in the population. However, most people would argue that the conditionally missing at random assumption is more plausible when you incorporate auxiliary variables because we've expanded the range of the observed data contributing to the analysis. That concludes our quick tour of auxiliary variable models in Blimp. Of course, you can apply the same strategy to other types of models, including path and structural equation models and multi-level models as well. Thanks again for tuning in, and I hope you check out other videos.